Good afternoon, everybody. Welcome to Friday, September 6th, Physics 1410. Just a couple of reminders, bits and pieces for us to go through. We'll be trying out the iClickers momentarily, so hopefully you've all gone and found the iClicker app on your favorite device, your tablet, your laptop, your phone, what have you. The ID for the course, I've just written up here. It's on, of course, the Moodle site. It's in your course outline. However, it's sitting right here, okay? The Physics 1410, Physical Science, Fall Winter 1920. So I do encourage you to go in and open that up while we're going through these preliminaries. The Chapter 1 homework, of course, is up on the Mastering Physics website. Many of you have already started it. That's good. Many more of you need to at least log in and register. Okay? It's not due until Wednesday, 10 o'clock in the evening. But past experience, and some of you have already experienced this, is that something's going to go wrong with the registration process. And then you're going to be sending emails to me and to Pearson support and so on. Much better for that sort of email traffic, if it has to happen, it happens today rather than Wednesday at about 8 o'clock in the evening, because by that point in time you'll be a basket case. Okay? So try and log into the Mastering Physics site today, tomorrow, as early as you practically can. Utilize the license which is associated with either your textbook if you're buying it brand new, or standalone from the Pearson publication website. Okay? Register an account. Log in, create an account, register with the mastering code that you have, and then you will see this course. The course ID, again, is in the course outline, and you'll see on there a couple of practice activities, Mastering Physics Essentials, Physics Primer, just to get you into the swing of using Mastering Physics, but the Chapter 1 homework is indeed posted. It's due, as I said, not until 10 o'clock next Wednesday evening, but it has to be submitted by that point in time, because at 10:01 that amount will be zero, all of the answers will be released, and everybody has the opportunity to see how they went. Okay? So I do encourage you, get busy with the Mastering Physics. Even if you don't want to do the assignment yet until, say, Tuesday or what have you, after the Monday lecture, that's fine, but go through the motions of getting yourself registered and find the course. Okay? There is a tutorial next Tuesday, 12:30 to 1:30 over in the Lassonde building, room A. I will be posting onto the Moodle site probably tomorrow morning the questions that we will go through. I encourage you to do them beforehand. These are practice questions. Do them beforehand. We'll go through them, answer questions, talk about any of the difficult concepts that you've had next Tuesday. Okay? Now, as promised, I launched an email through the announcement last night. Did anybody in here not receive an announcement broadcast from me last night? Would it come to your primary email address? Did anybody not receive it? Okay. Did you enroll in the course in the last 48 hours? That's probably why. Takes 48 hours-ish to get you into the system. Okay? Keep looking on the Moodle site. The announcements are all archived there. If you're still not in by, say, Monday, because you certainly should be in by Monday, send me an email to physics1410@yorku.ca with name, student number, and we'll find out why you're so special that you're not into the Moodle site. And that's a statement for any of the other folks here. If you have enrolled in the last 24 to 48 hours, your Moodle access may not yet have been granted. Okay? So give it another day or so. If you did not receive an email from me last night, send an email to physics1410@yorku.ca, student name, student number, saying, didn't see your words of wisdom on my email account, and you have checked your primary email account, and we'll get to the bottom of what the issue is. Okay? So if you've enlisted, enrolled late, give it another day or so. Okay? Okay? Because that definitely is going to be a problem at this time of the year. Processing people, getting you access. You'd think it would be automatic, but yeah, it's not quite automatic. The speed of light's a bit slow at York in the first week of September. Okay? Right. Okay, so let's see whether or not you've all found your iClicker account. Okay. So let's move this over here so we can all see. And okay. Right, given the fact that there's something like 200 people in the room and there's only 95 and counting, okay, please attempt to log into your iClicker account. It's not crucial today, but I'd like to try and get everybody on the right page today. Any mobile device should allow you access to the iClicker programming. Once you're in there, you look for York University. That should bring up a list of courses, and then you can either search for me, Delaney, or you can search for that or any subset of that, and that should bring up the course. And then you hit the big plus sign, big friendly plus sign, and that adds that course into your profile. That's the way it's supposed to work at any rate. Slow and steady wins the race here. Okay, we'll check back on that in a minute. We'll just, it was downloading and activating it and so on and so forth. We'll just put this up in the corner here to keep an eye on the number and let us carry on for the time being. We'll get to a clicker question once it looks like everybody is in. You recall last time we spoke about three fundamental quantities associated with physics: mass, length, and time. And when we start dealing with equations and constants, the notion of dimensional analysis will become important. That is to say, comparing apples to apples, adding apples to apples. If something is a length, then you add lengths with lengths. You don't add lengths with time, and so on. Being appreciative of these three fundamental or intrinsic quantities is really important. We spoke about the way we measure time, because the intrinsic unit of time, fundamental unit of time, is the second. And we spoke last time about how now we relate a second to something that we can measure in the laboratory. It's not an easy measurement, but nonetheless it can be done anywhere. Grab a cesium atom, allow the electron to flip its spin from one hyperfine state of the ground state level to another. That occurs at a very, very specific frequency. It's in the microwave region of the electromagnetic spectrum. When you've got light of that particular frequency, it therefore obviously has a period associated with it, and it means a certain number of periods will elapse to generate 1 second. Very, very accurate measurement, and it's reproducible, repeatable anywhere on the planet if you've got the right equipment. In a similar way, the fundamental unit of length, while it used to be sort of chunk of metal sitting around in a museum, Bureau of Standards in Paris, no longer. Now we actually can go ahead and, utilizing the idea of the speed of light in a vacuum as an absolute constant. Remember, speed is distance traveled over time taken. If we know how to define accurately a second, then knowing the speed of light to terrific accuracy, 9 significant figures here, 792,458 meters every single second. It's about 7.5 times around the Earth's equator, by the way, in 1 second. If we know that speed to that level of accuracy, in 1 second, we have traveled that many meters, so we obviously can define the distance of a meter in an observational, practical manner. The last fundamental quantity, mass, again, used to be a mass of material sitting in the Bureau of Standards. But everybody can't go over to Paris and pick this thing up and say, oh, okay, that's what a kilogram is, because it's not convenient. Rather, we're now in an age where we can go through and make these measurements in a laboratory. This time, we utilize something called Planck's constant. Now, you're perhaps not familiar with Planck's constant yet. Very fundamental constant when we start talking about electromagnetism, relating the energy that is carried by the photons of a certain frequency. For the moment, don't worry about that. The important point is we can define Planck's constant with great accuracy, just like we could define the speed of light with great accuracy. And you'll notice that the units, the dimensions associated with Planck's constant are kilograms, meters squared per second. Well, we know how to define a second with great accuracy. We know how to define a meter with great accuracy. We can therefore proceed ahead and create a physical experiment that will allow us to isolate the kilogram with great accuracy. And so 1 kilogram can be found now with great accuracy based upon the knowledge that we have defined Planck's constant to whatever that number of significant figures is, a very large number. So the 3 fundamental quantities of length, mass, and time can all be experimentally verified. And so the meter, the kilogram, and the second are now well defined. Of course, 1 second, 2 seconds, an hour, 100 hours, 3 years. When we start talking about large quantities of seconds or kilograms or meters, it's not convenient to just start writing them out longhand. And so we use what we call power of 10 notation. And so something that you will need to become familiar with are these types of abbreviations. So for example, we're talking about 1 gram. 1,000 grams in a kilogram, so 1 gram is 10 to the minus 3 kilograms. You've likely seen all of these abbreviations at one time or another. You're going to see them lots as we work our way through this course, because of course lots of things are really big or really small and necessitate the use of these types of short form abbreviations. So a nanosecond, 10 to the minus 9 of a second, that's 1 billionth of a second, and so on. There's a nice little table right here that I will make sure that you have available to you on the exams and the tests and so on, but I do encourage you to become quite fluent, quite conversant with the various short forms for large powers of 10 and small powers of 10. Let me just back up here for a second. Power of 10 notation, again, is something that you're going to utilize a lot. Whether or not you have used it much in the past, trust me, thank you, trust me on this, you are going to utilize power of 10 notation a lot. Because when it comes to the very big and the very small, it's the only short form that is going to be practical for you to work with. And so when we look at objects that are around the place, all the way from, distances between galaxies measured in millions, if not billions of light years, and therefore lots and lots and lots of meters or kilometers, through to the size of the sun or the size of the earth, tens of thousands to hundreds of thousands of kilometers, to the height that you are of order a couple of meters. Those are the large end of the scale. All the way down to looking at atoms and molecules that are a tiny, tiny fraction. When we start looking at the diameter of the nucleus, for example, we're down around about 10 to the minus 14 of a meter. Really, really small values. So power of 10 notation, that short form, and how to manipulate numbers, that are in scientific notation, I urge you to become conversant with. And there's lots of questions in the back of your chapter that will help you with that. I believe there's an appendix at the back of the textbook that will give you some additional insights and so on. Okay. When you're creating, when you're answering a problem, you're creating a methodology to solve it. And we'll talk about that methodology very shortly. But when you get to the end and you've got an answer, don't always assume that that answer is, what it should be. Having an appreciation of what the answer should be, not with any great significance, but ballpark figure, is important. And as a consequence of this, I encourage you to sharpen your ability to make good estimates. These types of back-of-the-envelope calculations or Fermi question type calculations, very, very useful to you as a physicist. Trying to figure out, for example, how many hairs on a cat, how many drops of water are in the ocean, how many grains of sand are on the beaches of the world. Those are answers that you do not readily have. But you can go ahead and make various approximations to gain an insight into the sort of answer, the magnitude of the answer that you would expect. So being able to look at a problem, do a quick calculation based upon, round off that number to 10, round that number off to 100, round that number off to whatever, and so on. And then doing a quick calculation in powers of 10, again, it's a very helpful tool for you to have, especially as you work through a variety of differing physical problems. Now, I said to you before, dimensional analysis is really important. Units are very important. When we're doing problems, it's really important for you to recognize the fact that maybe some of the variables that are in this problem aren't in the same unit. So, for example, if I am talking to you about determining, for example, how long it takes to go from A to B, and I give you a distance in, let's say, meters, but I give you a speed in kilometers per hour, and I ask you for an answer in seconds, there's a lot of differing units inside that problem. If you start in with the speed is distance traveled over time taken, and don't pay attention to the differing units that I've just cited, trust me, you're going to get the wrong answer. So it's important to be able to line up all of your information and ensure that the differing units come into accord with each other. If you will, deal with apples and apples. So, simple example, 3 minutes. If in fact you know that you need to be working with that unit of time, not in minutes, but in seconds, then you need to have a conversion factor available to you that will move your initial information out of the units of minutes into the units of seconds. And so you would write down, in this particular instance, 3 minutes of time. How many seconds exist in a minute? 60 over 1. Go ahead, and as you can fairly straightforwardly see, the minutes disappear, if you will, so they cross each other out, and you're left with 3 times 60 to give you the 180 seconds. Simple example, you all know that. Trust me, there will be examples where the conversion is not quite so obvious. Being confident of the way you convert one unit into another, again, very important. These are the basics. You're going to be dealing with problems where you have to think very carefully about the procedure. That will be the hard part. The last thing you want is to trip up on multiplication or division of unlike units. You want to make sure that you know how to convert one set of units into another so that they work seamlessly within the problem that you are trying to solve. Okay. Accuracy. Whenever we make a physical measurement, it is not 100% accurate. There is always error that is associated with it. There is some measure of inaccuracy associated with any physical measurement. And sometimes that inaccuracy, that error, is quite significant. So we're referring to here, for example, third bullet point down, 23.65 plus or minus 0.02. What that is saying to you is that we anticipate that the real answer to whatever this measurement is lies somewhere between 23.63 and 23.67. It's a reasonably accurate number, 23.65. The error is quite small with respect to the actual number, but nonetheless, 23.65 is not necessarily the correct answer, but within plus or minus 0.02, we do expect the accurate answer to exist. So accuracy is something we're always striving for. We are always appreciating the errors that exist in our physical measurements. And obviously, the more the physical measurements are that go into a particular observation, it is a higher uncertainty that will exist with your final answer. So bear in mind, accuracy and error, uncertainty, go hand in hand. Even worse, even worse is the idea that accuracy and precision are not the same thing. You can have a very precise readout, which is not particularly accurate. And conversely, you can have something which is very accurately operating, but your ability to precisely read out that information is compromised. I'll give you an example in just a second here. When we're looking at any number with uncertainty, then there is this notion of significant figures. So that 23.65, for example, is a number that has with it 4 significant figures. The error lies, obviously, in the second digit to the right of the decimal place. Giving me an answer that is, for example, 23.636, that third decimal place, the information carried in that third decimal place is irrelevant. I do not have that measure of accuracy available to me. My accuracy lies in that second digit. Quoting me a third digit is not only pointless, but just plain fact wrong. So keeping an eye on the significant figures that are available to you, reflecting how confident you are in the accuracy of your answer, you've just got to keep track of it. Now, here's a wonderful little example here. Train might go clear across the country, thousands and thousands of kilometers, and therefore hundreds of thousands of meters. If the error in its distance going from A to B is a very, very tiny margin, a percentage that is, say, like less than 1%, well, that's fine, but 1% of 1,000 kilometers is around about 10 kilometers. Well, most railway stations don't have that excess amount of track if your percentage error for the distance you're traveling is in fact as high as 1%. Apparently, this is a real image where somebody didn't quite do all the arithmetic properly, and the train did in fact plow through the stop at the end of the railway station. So, measurement and the associated uncertainty can be really, really important. When we're talking about significant figures, the multiplication of numbers. So if you've got 2 numbers with a certain amount of significant figures, you cannot have an answer that is more accurate than the least accurate number that you're using in your multiplication or division. So, for example, if you've got a number that has got 3 significant figures and you're multiplying it by a number that has 2 significant figures, your answer cannot have more than 2 significant figures in it. If you're doing addition, subtraction, then the significant figures to the right of the decimal point is what counts. You might have a number that is 5, 6, or 7 significant figures of original accuracy, but if only, say, for example, 2 of them are to the right of the decimal point, then that is an important piece of information with respect to the total accuracy, the total number of significant figures that you can have in your final answer. If you've got two numbers that you're adding together, two significant figures to the right of the decimal point, and the other number has three significant figures to the right of the decimal point, your final answer can't be more accurately than the least accurate of your information, which in this instance is two significant figures to the right of the decimal point. Okay, so let's look at an example so that you don't have to remember all of those things. In this particular instance, for multiplication, we have three numbers that we're either multiplying or dividing. We have a number, three significant figures, the 0.745. The 2.2 obviously has two significant figures, and then the 3.885, four significant figures. You multiply them all together, the least well-known, the least accurate number within that calculation has two significant figures. Therefore, your final answer cannot have more than two significant figures. Your calculator will give you 10 significant figures. Your calculator is irrelevant in this regard. You as the human need to assess where the significant figures stop in your answer. For addition and subtraction, for example, you have again three numbers at the bottom there, five significant figures, four significant figures, four significant figures, but it's the information to the right of the decimal point which counts. You've got three significant figures to the right of the decimal place for the first number, the 0.153. You have one significant figure to the right of the decimal point for the next number, 0.2, and then the 0.74 has two significant figures to the right. You add and subtract, you do all of the work. Your final answer cannot be more accurate than the least accurate number there. That is to say, in this instance, the significant figures to the right of the decimal point, the middle number there, one significant figure to the right of the decimal point. Therefore, your final answer cannot have more than one significant figure to the right of the decimal point. Okay? So, significant figures talk to you about the accuracy of your observations. Now, I said to you that accuracy and precision are not necessarily the same thing. You certainly strive for a measurement that is in equal measure accurate and precise. That's the hallmark of a good observation. However, you've probably all got digital clock radios, or you pull out your cell phones and your cell phone gives you information that is accurate to probably a fraction of a second, probably a tenth of a second. There is great precision in the information that those devices are giving you. It doesn't necessarily tell you anything about the accuracy. That is to say, how well is time being kept by those devices? I can precisely read out a number, 3 hours, 16 minutes, 22.22 seconds. But if that device is losing an hour a day, that level of precision that I just quoted you is completely bogus. It's completely irrelevant. Equally, if you've got an analog device, say an old clock with hours and minutes hands, and you know that that clock is superbly accurate, but you can't read off the time more accurately than, say, the nearest minute because the second hand has fallen off and it's broken, then telling me that it's 13 minutes past the hour, even if you know that you should be able to have a greater precision associated with that number, you just can't read it. So precision and accuracy are subtly but importantly different. It is the marriage of accuracy and precision that represent the hallmark of a good observation. Okay, how many people have managed to fight their way through the iClicker situation? 137 of you. There is more than 137 of you in the room. Okay, so many of you obviously having difficulty finding that iClicker account. Remember, it is worth marks, not today, but when we ask questions, if you're throwing them away, if you're blowing them off, not a good plan. Let's, a few more of you find your iClicker account. Probably a bit of a recap for many of you in the room, the difference between scalar quantities and vector quantities. Scalar quantities are literally just numbers. With units, remember units are really important, but it is just a number. Speed limit through a school crossing, 30 kilometers an hour. The cost of bananas at the local store, 57 cents per kilogram. Pretty cheap, actually. Scalar quantities. It's just a number with the units attached to it. Quantities. By contrast, vectors have that scalar quantity, or a scalar quantity, but a defined direction. So if you are in a car and you're traveling at 50 kilometers per hour north, that is a vector quantity. It is a defined scalar value associated with your speed, but I have defined as well the direction, and therefore that is considered a vector quantity. Vector quantities have scalars and direction. Both must be present. Okay? Temperature is a scalar quantity. Wind is a vector quantity because you normally define wind with both a speed and a direction. There's lots of differing ways or nomenclatures to define, draw attention to a vector. In this book in particular, it tends to be a value, a symbol, which is bold-faced, and there's a little squiggly line above it. Other textbooks that you might be referring to have got little squiggly lines underneath. Just depends on the nomenclature. There's no right way or wrong way. But you will find in my notes, because they're mirroring the University Physics textbook by Friedman and Young, that bold-faced and squiggly lines above represent vector quantities. The magnitude or the scalar portion of that vector, straight lines around the vector, okay, normally with the bold-faced disappearing. So the value, the scalar value of a vector quantity often is encapsulated within these vertical lines. That's the magnitude of it. Okay? The distance between 2 points, so grab any 2 points on your number line, grab any 2 points in your environment. As you go from one point to another, we can define both a displacement that has taken place in that movement and a distance that has been traversed. They are not necessarily the same values. The scalar portion of that vector is not necessarily the equivalent to the scalar value of distance. We certainly know that the vector giving a displacement and a direction, both quantities needed, but the scalar value of a vector, its displacement, is not necessarily the same as its distance. We'll show you why. So going from point 1 to point 2, any two arbitrary points. Because we are going from point 1 to point 2, then we define the direction to be, as shown here, as the arrow moving from point 1 to point 2. That is the direction, more or less northeast. Okay? We can define it with an angle, but not fussed at the moment. Point I make is moving from point 1 to point 2. That defines the vector. There is a displacement associated with that vector, vector A, and we could go ahead and measure the length of that vector, that arrow, from point 1 to point 2, measure it, and that would be the scalar value of the displacement associated with that movement. So vectors have a head and a tail associated with them. If I go from that same point 1 to point 2, and I have a bit of an erratic path, I get lost through the woods, I meander around for a while, but I eventually get to point 2, my displacement is no different than it was before if I walked directly from point 1 to point 2. The displacement is the same. This displacement, as you can see, from point 1 to point 2, is defined by the vector A. But because I was lost going from point 1 to point 2, I traversed a considerably greater distance in the process of going from point 1 to point 2. The distance associated with that movement is a scalar quantity, significantly larger than the displacement that took place going from point 1 to point 2. distance and displacement can be very, very different. If I go from home to a pizza store, grab a pizza, and come home again, my displacement is 0. The speed with which I have been traversing that little exercise is, sorry, not the speed, the vector quantity of velocity in that movement is 0. But I obviously drove to the pizza store and I drove back home. I traversed a distance and I took time to do it. I therefore had a non-zero speed, but my displacement was 0, and therefore my velocity in that example was 0. Displacement and distance are different. Same thing, just what I said. Okay, so like vectors, going from point 1 to point 2, going from point 3 to point 4, those two vectors are identical. They have the same scalar distance, and they have the same direction. They are parallel to each other. I don't have to line them up neatly like that. I could put that second vector anywhere else on the page, as long as it's going in the same direction and has the same scalar length as P1 to P2, then wherever P3 and P4 are, doesn't matter. They don't have to be side by side. Same vectors. If, however, I define a vector that is in the opposite direction, so instead of going from P1 to P2, but in this instance going from sort of P3 to, well, as you can see, P5 and 6. Oh, okay, fine. Confuse me. So in this particular instance, the vector B is in the opposite sense to vector A. Well, we can define B as minus A. The length, the scalar length, hasn't changed. But the direction is 180 degrees opposite to what it was before. Okay? So vectors have a variety of differing qualities, if you will, that you probably have seen before, and this is probably stuff that you've all gone through before, but that's okay. We'll go through it again reasonably quickly. Okay? So in this particular instance, if we added A to B, the net effect would be 0. Okay? Wouldn't go anywhere because B backtracks on A. Assume that A and B are not exactly opposite as I had just shown, but rather any two vectors A and B defined as a head-to-tail type operation, so they have a scalar length associated with each of A and B. They have directions as defined. You can go ahead and do vector arithmetic, add A to B, and end up, surprise, surprise, with vector C. Adding head to tail, tail to head, there are a number of differing ways you can go about graphically adding vectors. Whatever way you were taught at high school, I'm not going to override it. But the net effect is that as you draw vectors with tails and heads, you are effectively being able to add them together graphically. We'll talk about adding them together numerically in a moment, but graphically speaking, you can go ahead and add vectors A and B in this fashion. Tail to head, resulting vector being from the original tail to the resulting head. So C, in this particular case, is defined from a vector perspective as A plus B. Doesn't matter whether or not you add vectors A plus B or B plus A. It's a commutative process. The order doesn't matter. Okay? And so here we've got the same resulting vector C. B plus A has worked out to be identical to A plus B. So adding the vectors commutatively is just fine. Some of you might like to add your vectors in this manner. Put all of your vectors with their tails together, draw a parallelogram, and then the long axis of the parallelogram gives you your resulting vector. Fine. Not fussed. Don't care. Whatever way you learn to add vectors together is just fine by me. If two vectors, A and B, are parallel, as in this particular instance, then obviously, I hope obviously, if I add the scalar quantities, the length of A to the length of B, then the lengths, the distances, are equivalent to their displacements. So A plus B, if A has sort of 5 units of length and B has 6 units of length, then I could actually go ahead and say, well, gosh, C is going to be 5 plus 6, it's 11. It only works because A and B are parallel. Don't assume that you can go ahead and add the scalar lengths of vectors numerically. Okay? Works as long as they're parallel. It won't work in general because, of course, more often than not, the vectors are not parallel. So just be careful as you're playing with things. Obviously, if in this particular instance you have two vectors A and B and they're anti-parallel, well, okay, you can certainly still come up to the conclusion that the resulting vector C is in fact still going to be A plus B in terms of their lengths, because B, of course, is acting in the opposite direction. It's the negative direction. It's anti-parallel. The parallel and the anti-parallel options are not the normal options. Normally, vectors A and B will be at an angle to each other, and therefore determining what the resulting distance is for the resulting vector C requires a little bit of trigonometry, a little bit of numerical work to determine what that answer is. Or, of course, if you're very accurately drawing things to scale, okay, you can go ahead and measure the resulting vector to scale. But when they're parallel and anti-parallel, you've got luck on your side. You can do a quick short form and do the arithmetic as far as their values, their scalar values are concerned. Of course, we can go further. You can add multiple vectors because that's more often the situation. A, B, and C. Go ahead and add tail to head, tail to head, tail to head. Again, however you were shown how to do it in high school, you grab two of the vectors together to get a resultant, and then you add that resultant to the third vector, and you get a new resultant. It's fine. Just be careful the way you add them graphically. Okay? This is another way of doing it. Okay? Just add them all. Don't take any intermediate resultants. Just add A to B to C, and your resultant is obviously from the tail of A to the head of C. It doesn't matter the order because vector addition is commutative. A plus B plus C is the same as A plus C plus B, or B plus C plus A, okay, whatever. Again, all sorts of stuff that you've probably seen before, which is why I'm skipping along through it. This is not stuff that I should be teaching you as such.
I just can't remember. So what happens if the new vector you're driving overlaps other vectors? Okay.
Doesn't matter in the slightest. Okay. Now, as I say, if you're now doing vector arithmetic and there's negatives involved, okay, be a little bit more careful because A minus B versus minus B plus A, okay, it's not a commutative type reaction or interaction. So go ahead and, as we've got here, you've got A charging off to the left. You've got B, which is charging towards the lower left-hand side, but you're now doing a subtraction from A minus B. You can see at the bottom the way you can proceed ahead and do that. You can certainly grab minus the B vector, flip it around so that's plus. You're adding the minus B. That's nomenclature, which is going to get me into trouble somewhere along the line, but you can see it at the top there, that the minus B vector can be flipped around, and if you find that easier to work with when you're doing your vector arithmetic, again, it's fine. However you have learned to add vectors, whatever your comfort level is with respect to differing vector additions and subtractions, that's fine. Scalar quantities. You can multiply up vectors. So if you've got a vector of a certain length and it's multiplied by a scalar quantity, you still end up with a vector. So 2 times vector A, 3 times vector A, minus 2 times vector A. You can go ahead and multiply that scalar onto your vector. You still end up with a vector quantity. If there are minus signs involved, just be careful. Obviously, the minus sign basically says you're reversing direction. Just like on your number line. If you're moving in the positive x direction, moving along quite merrily, and all of a sudden we say reverse your direction, well, now you're moving in the negative x direction. Okay? So minus of the scalar doesn't change the arithmetic value, it just changes the sense or the direction. Okay? So as you can see at the top, okay, 3 times vector A versus minus 3 times vector A at the bottom. The minus sign imposes a change, a 180-degree change in direction associated with the vector. But the value, if you will, the scalar quantity associated with the length of the new vector, it's the same in both cases, 6 units or whatever it is, but in one case the direction is 180 degrees opposite to the other. Now when we look at vectors, we can actually define vector components. Here we have a run-of-the-mill everyday vector, and there are 2 orthogonal components that are associated with that vector. A component that is parallel to the x-axis and a component that is parallel to the y-axis. So A sub x, A sub y. Any vector can be broken down into components. Now in this particular instance, we're in a 2-dimensional situation. Okay? The page, the screen, what have you, it's a 2-dimensional situation. 2 components associated with that vector, the x and the y component. And we'll touch on 3-dimensional situations where there will be a z component, but later. 2 components, ax and ay, associated with this vector. They're giving an example in this particular instance associated with sort of, orienteering, going along an x direction, going along a y direction is equivalent to that resulting vector, the blue line, if you will. And we can always measure not only the distance it's traveled, but theta, an angle that is defining where the resulting vector is pointing. Okay? So you can take any vector in 2 dimensions and have an x and a y component that is associated with that vector. In general terms, remember your trigonometry. Sines, cosines, tangents, when we're talking about vectors, very, very useful. Sine is opposite over your hypotenuse. Cosine is adjacent over your hypotenuse. Tangent is your opposite over your adjacent sine. All that sort of good stuff that I'm sure you remember from high school. When we're talking about a vector, in this particular instance A, it has an ax component, which is obviously a cosine theta, and it's got a y component, which is the length of the vector A times the sine of the angle, and the angle is so defined there as theta. By definition, we normally define an angle associated with a vector to be measured counterclockwise from the positive x-axis. So here we've got the origin O. You can see the x-axis, the positive x-axis, screaming off to the right. You can see the positive y-axis dashing upwards across the screen. The angle theta is measured from the positive x-axis counterclockwise round to the vector A. Looks like about 30 or 40 degrees. Here. Be careful when you're measuring angles, because you will have vectors that are not always pointing off in the positive direction in this manner. We'll often have them in any of the 4 quadrants, and therefore keeping an eye on what the angle is for definition will be important, as in this particular instance. Obviously, we've got a vector which is charging off in the negative x-axis direction. We can still define a component in the x direction. We can still define a component in the y direction. But the angle that helps define this vector, and you have to define a direction. The angle theta there is still measured from the positive x-axis counterclockwise, but obviously now is greater than 90 degrees. Okay, I'm going to stop there. You have 145 people who have looked in on the iClickers. On Monday, that number needs to be much closer to 250, or you're going to be really annoyed at losing marks. So, have a good weekend, folks. We'll see you on Monday.